Hi, this is Lesson 5 in Polynomials, and now we're going to look at solving them. So far we've been factorising, showing that things are factors. We're going to go this wee step further and actually solve them now and find the roots of a polynomial. So here's question 1. We want to find the roots of this polynomial here. Now, back in National 5, remember the roots were the points on the x-axis where the curve cuts. Okay, so it's the exact same here, but because we've got a cubic function, we are probably looking for maybe 2 or 3 answers here, okay, for roots. And it's pretty similar to National 5. In National 5, you would factorise, get your brackets, and then solve each of your brackets equal to 0. We do the exact same thing here, only to factorise, we have to do our lovely nested table. So that's where we're going to start in this one. So nested table. There is no missing coefficients, so we always check that first. So let's put in our numbers. So the little trick I normally do is if the coefficients add up to 0, then I can use 1. That doesn't apply here. Now, you can play about for ages trying to get numbers to work. I'm going to start by using -1 and then see how we go from there. So with -1, bring down the 2. That gives me -2, which is -17, plus 17. Oh, that's 30 something, that's far too big. My next option, I'm just going to work my way up. I'm going to try +2 now. So 2 times 2 is 4, 4 taken away 15 is minus 11. That then gives me minus 22. 16 add -22 is -6. Double that is -12. Oh, that only took me 2 goes there. I actually tell a lie. It took me a few goes. I paused the video and came back and knew that 2 worked. Anyway, we've got it, right? So then we can say, right, okay, remainder is 0. So x minus 2 is a factor. Okay, so let's factorise. So we have x minus 2, and then our quotient is 2x squared minus 11x minus 6. And it said equal 0 up here in the top right hand side, so I can put this equal to 0. Let's factorise this, so 2x and x. Numbers multiply to 6 and add to 11. I'm reckoning this as a 6 and a 1. If I put the 6 here and a 1 there, that gives me 12 for the outside numbers, 1 for the inside. That'll work. So it's got to be -12 and plus 1. Now from there you do exactly what you did at National 5. You put each bracket equal to 0. Now I know some of you will skip this line, but for the sake of my video I'm putting it in. So you do each little thing equal to 0, like that, and then solve them. So you get x equals 2, x equals -1/2, and x equals 6. So that is the 3 roots of the equation. If they ask for them as coordinates of where it cuts the x-axis instead, you would write them as coordinates 2, 0, -1/2, 0, and 6, 0, and so on. Okay, so next question. So in this question, you're asked to find the coordinate of the point of intersection of the curve and a line. So a cubic curve looks a bit like this, potentially. Okay, there are other shapes available. And we have a straight line that is intersecting it. Now, my straight line could be intersecting in 1, 2, or 3 places here. So there's going to be multiple answers. Now at National 5, you would have use simultaneous equations for points of intersection. We can't do that here, right? At higher, we have to do something else. So for points of intersection at higher, we do something called setting y equal to y. Okay, now you were probably taught simultaneous equations to eliminate a letter. There is another method called the substitution method, and that's effectively what we're doing here. We've got 2 different equations that both say y equals and y equals. So effectively what we're really doing is substituting in this thing here, the 2x minus 1, for this y over here. Because if y equals y and y equals y, then these 2 things are equal. So that's what we're going to do. But because I've got the x cubed, I'm going to put that one on the left hand side. So this is what we're going to do. So I'm putting the one with the highest power on the left. So you put both equations equal to each other. Then you bring everything to the one side. So that's why I put this one on the left. And minus 5, negative 2 gives us negative 7. And negative 11 plus 1 is negative 10. Now, to move on from here, we basically have to factorise what we have. But you can't factorise it until you've got everything to one side and equal to 0. Okay? So we're going to go do our nested table. We have 1, 4, negative 7 and negative 10. So again, we have to play about with numbers that multiply to 10. My little trick doesn't work here because they don't add to 0, so I'm going to start with minus 1. Bring down the 1, that gives us negative 1. That gives us 3. Multiplied by 1 is negative 3. This gives me minus 10. Oh, I got it first time. Brilliant. So this is what we have. So because our remainder is 0, we know that we have our first factor. Now it's minus 1 in front of the table, so that becomes plus 1 when we write it as a factor. So what we can do now is we can rewrite out our polynomial. We've partially factorised it. So your first factor is x plus 1. Then you do your quotient, x squared plus 3x minus 10. I don't know why I said 11. Equals 0. We're going to factorise the quotient. Numbers that multiply to 10 and add to 3 are a 5 and a 2. To get positive 3, it's going to have to be plus 5 minus 2. So we have now factorised our polynomial. What we do from here is we then solve it, each bit equal to 0. So the first one gives us minus 1. The second one gives us minus 5. And the last one, oh, I forgot my x, gives us x equals 2. Now the question said, find the points of intersection of the curve and the line. Whereas my previous question just wanted the roots, which means we would be done here. But we need coordinates. So the question is, how on earth do you get the other part of the coordinates? You have an option. You can substitute each of these x values into either the equation, which means substituting into 4 things, or the line, which means substituting into 2. Choose wisely. We're going to use the line. So into the equation, y equals 2x minus 1. We're going to sub in each of these numbers. Now, so for the first one, if we use a coordinate minus 1, when we sub that in, that gives us minus 2 minus 1, so minus 3 for our first coordinate. When we sub in minus 5, that gives us minus 10 minus 1, which is minus 11 for our second coordinate. And on the last one, when you sub in 2, that gives us 4 minus 1, which is 3. So they are your coordinates there. Okay, and that's that question solved. Now my third and final style of question brings in a little bit of the question from the other day, where we have an unknown coefficient. We have to find the coefficient and then fully factorise and then find the roots. So it's exactly the same as examples in lesson 5, but we do that extra bit at the end. And luckily they've told us x equals 1 is a root. Now watch, because they normally tell you that something is a factor. So because they've told us a root this time, the root is a number in the table. So we can put in the number 1. So our coefficients would be 1, minus 4, 5 and k. If you've been paying attention, my little trick says that if you can use the number 1 in front of the table as a root, then all these numbers must add to 0. So I've got a little bit that says k is going to be minus 2, because at the moment I've got 6 take away 4, which is 2. So I need to have another take away 2. However, we need to do the working, but it's just that little trick helps sometimes. So bring down the number 1. 1 times 1 is 1. 1 take away 4 is minus 3. 5 take away 3 is 2. So at the end I get k plus 2. Now because x equals 1 is a root, I know that my remainder equals 0. So I can put k plus 2 equal to 0, and lo and behold, k comes out as negative 2. So I've done the first bit of the question. Now I need to fully factorise. So fully factorising it gives us x, positive 1 in the table becomes minus 1 for your factor. Your quotient is x squared minus 3x plus 2, all equal to 0. A wee bit of factorising again. This is an easy one. Numbers that multiply to 2 are 2 and 1. And to get minus 3, they both must be minus. And then we solve that and you get x equals 1, x equals 2, and x equals 1 again. So basically what we have here is we have a repeated root. Now, just to explain what that means is, remember what a repeated root meant at National 5? It meant that your curve was touching the axis, right? Now, it's very similar here in a polynomial. What we have potentially is something shaped a bit like this, and maybe, no, that's a lie. It would look better if I did it this way. So something maybe shaped like that, where we have a root here at 1, where it's just sitting on the axis, and we have a root here at 2, where it's actually cutting through. So x equals 1 repeated means that it's a touching point, but you see more of that later on. Now, if you have access to the TJ textbook, these are the questions I would recommend doing. I've just picked and chosen some from the exercise that follow what we've been doing. So the first couple apply to example 1. Question 6 applies to example 2, that's the point of intersection 1. And then the last couple all apply to example 3. So hopefully this has helped. Good luck. Bye-bye.